Okay. So as I said in the last class, we will first define what one neuron is. Okay. So let me write the definition. An artificial neuron. So I'm using an artificial neuron. So I'm defining one neuron. Okay. So an artificial neuron with, so in this whole deep learning stuff, we have something called as weights. Okay, I'll come to it. With weights. So how many weights? So let me take say n weights. W1, W2, dot, Wn. So I take n weights, and these weights, they belong to real number. So I write this complicated mathematical way of saying that it belongs to real number. Well, math symbols are basically like they don't want to write much, so that's why they use symbols. So it belongs to R. So these are the weights. And then we have something called as bias. Here let me take a bias of W naught. Okay. This also belongs to R, so it's a real number. And there is something called as activation function. So forget the word activation and focus on the word function. So basically, it clearly indicates there is some function which is hidden in the artificial neuron. So now you have your first hint what a neuron is. So basically, each neuron is home of a function. So some function is hidden in it. So let the activation function G, so let it be G. Now what a function is, by definition a function is, it takes some input, say it belongs to real number, and it gives you an output which also belongs to a real number set. So this is just the mathematical jargon, you can skip it. So an activation function G, so it contains that. Okay, so it has weights in it, biases in it, activation function in it, and the combination of all these weight, bias, and activation function is so let's see. So an artificial neuron is, you can also read like this. So an artificial neuron is, so what it is defined as a function. So this is the final thing that you get out of one neuron. Is defined as a function h. Again, the function h will take in all the inputs. So we have n inputs here. So n input feature. So I'm writing a definition for some data set that takes in n input feature. In our data set, we have one input feature. So this n will become 1 for the case that we are considering here. But anyways, let's write it in a more generalized way. Rn to R. So again, so this is the definition. So some function h is hidden in this neuron. Now what this h takes in? So h takes in many inputs. So here in this case, the h takes in only one input. But in a more general case, the h will take in into, say, here in the definition I said earlier that we are taking an input, xn. So this can be written in a more simplified manner like a capital X. So the capital X holds the information of how many inputs you are giving. Okay. Now what is this h of x? So it eats. So h is a function. So every function eats something. So it eats the input and throws out the outputs. Here it is eating the n input. And how it is eating the input, that's important. It is eating these inputs through an activation function G, and it is not eating the inputs directly. It is kind of making a linear combination of the input and then adding a bias and then eating it all. So that is its sum J goes from 1 to n. So this may look scary, but this will be simplified as we continue in our example. So this is what H is. I can bring in some more mathematical notation here, to simplify this writing. So this can also be written, in a very nice form, in a dot product form. W dot x. So x is, one. You can treat x as a vector. So x is like a vector that contains this x1, x2, dot xn, and w is also a vector that contains all of it, but we'll not go through this because we have not started these things yet. So let's not even try to simplify it as of now. Let's keep it complicated. Now what we will do is we will try to break the whole thing down for our simplified deep learning. I need a new color, maybe this color. Yeah, the gray one. So here what we have, a special case. So what is a special case we have considered? So let's try to do it case by case. Okay. So the first case. So this is the case one. So what we have done in the case one, well, to understand it, we took one input and one neuron. Now you will see why I'm doing this, why I'm taking one input and one neuron, because in the beginning of the lecture I was talking about linear regression. Okay, that's why things will become clear as we go further. So when you have, one input, then your h will be a function of only x1. That's clear, right? Okay. This can be written as this is equals to g. Okay, you have only one input, so there will be only one weight. So w1 x1, and there will be one bias w0 that will get into this g. So fundamentally in the diagram, so you have, your input x1 sitting inside it, and when it goes inside the neuron, we take not x1 but some weight multiplied with x1, and then we put it inside h along with a bias w0, and the activation function is here. So let me write the activation function sitting here. So what is g? G can be, many functions, but let us assume that the function g is just something like whatever it eats, it gives out. Okay, any simple function. So if it eats w1 x1 and gives out the same, then h1 of x1 is this. So so h is w1 x1. So when the h goes out, so from here the h is going out, then the final h that reaches the output. Know that every neuron will produce some h which will go into the output. Okay, but now we are doing one neuron, so we'll not understand how the outputs of other neuron, how the functions in the other neuron they hit the output and what happens. We'll do that later on. But at this moment, the output that we are going to hit is h, and this is what you get. This kind of looks similar to what you might have done in linear regression. If you look closely, what do you find? You find your input here with some slope here and some intercept here. So As you can see, what we have done here is that if we take one layer where the activation function is none, we are not using any complicated activation function. There are many activation function, but we will not use that. We will use some activation function such that whatever it eats, it gives out. We do that. What happens? The output is like it is mimicking linear regression. Quite interestingly, it is mimicking linear regression. So thus, if we take one neuron with the activation function as none, so in the code you write activation function equals to none, then the whole simplified DL diagram that I have done here mimics the linear regression. So now what we can do is we can code the whole thing, and we can see it in fact. So we can code this whole diagram and all the mathematics that we have learned, and we'll try to find out what do we get.